Hello everyone, we're back with another episode of Computer Vision Talks, and today we are going to discuss federated learning and vision tasks with Umberto. Umberto is a PhD student at University of Padova, and he has been working in visual understanding across semantic groups, domain, and devices at University of Padova. He did his M.Sc from University of Padova itself, and he completed his master's thesis in TU Dresden, and has also been an intern at Samsung Research in London for 8 months. And we're going to explore all about federated learning. We'll begin with a primer and then delve deeper into papers that were recently published by Umberto. One of them were published in a CVPR workshop, and the other one is still under review. Am I right?
Yes, that's correct.
Okay, over to you. Please start.
Okay, so thank you very much for the introduction. So I guess I can start. Today's talk will be focused on federated learning and vision tasks, as you mentioned, and the work I will present today has been researched during an internship at Samsung Research UK. So, all right, so let me start with, sorry, I need to, okay. Yeah, so first of all, I would like to briefly introduce myself. I'm a final year PhD candidate, and my research interests have been lying in the intersection of three machine learning or deep learning tasks, which are continual learning, domain adaptation, and federated learning. All of them, of course, since I'm a vision guy, I applied them to vision tasks, right? And okay, so however, let's say the work that I will present today have been researched in Samsung, so I will focus on federated learning tasks. I've been in Samsung for roughly 8 months in the first European Research and Development Center at South Korea, and still one of the largest one at South Korea. And today's talk will be, let's say, the overview of today's talk will be something like this. First, we will focus on some background knowledge of federated learning. I will assume that most of you doesn't know what federated learning is, so I will really start from scratch. And then we will go through the targeted challenges that we want to tackle in our works with a special focus on visual feature representations. Then we will move to our two papers that are the main contributions that I will let's say explain today, which are fair averaging, published at a workshop at CVPR this year, and FedProto, which is on archive still under submission, let's say. For both of them, I will firstly briefly introduce the method, and then we will see some main results and analysis of those. Finally, I will conclude with some conclusions, with some thoughts. And yeah, please, if you have any questions, interrupt me or just drop a message in the chat or raise your hand, or I don't know, do something so I can.
So yeah, so if you have a question, you can drop it in the chat and I'll ask you. If you want, you can unmute and go ahead and discuss your questions till you're satisfied, or you can just post them. I'll read them out for you.
Yeah, thank you very much. Okay, so let's start with some background on federated learning. So federated learning, if you want a compact definition, is just distributed machine learning on heterogeneous dataset. And so let me start with the standard traditional centralized learning, where you have a set of devices and those devices acquire some data, then they send those data to some clouds, so some server, and then the server has one single model to, let's say, to be trained on the data acquired from the local devices. So in this case, devices acquire a ton of data, they send it to the server trains the model, and after training the model, the model is sent back to the devices, which can then use the trained model. In federated learning, this is pretty much the opposite, because we have many devices. Again, they acquire a lot of data, but then they don't send the data to the server side. And so what they do is simply to train the model locally on the device with the data acquired from the local devices themselves. So as we let's say introduce the problem like this, we can see that the privacy is better ensured because data never leaves the devices. There are no data breach risk, as again data are just present locally and they are not sent to the server. And by, let's say, Incidentally, we also have lower server costs since all the models are trained locally, and so the server just need to pull all the solutions sent from the local clients. Federated learning can also support multiple modalities, such as client to server or clients, and there can be some middle entities between clients and servers and so on. And finally, but not less importantly, we have that data are available in each local client. Since I don't know if you're familiar with, but in centralized training, or let's say in the standard learning, you have all the devices that can opt out from data sharing, right? On your phone, you can opt out from data sharing. So your local data should not, let's say, leave the device. So this is in federated learning, this is not an issue anymore, since all the data are stored only locally. All right, so you might argue that then federated learning is simply distributed learning, right? They just basically do the same thing. Well, this is true up to some extent, because both of them aim at training a single model on multiple nodes. But I think there are some key differences and between the two paradigms. So the difference that I see between those two paradigms is in the focus that they have. So while distributed learning wants to parallelize the computing power, so they want to maximize the compute as much as possible. In federated learning, instead, the focus is on training on heterogeneous datasets, because each of the client will acquire a different, will see a different domain, will acquire a different number of samples on each in each device, and so on and so forth. And so you don't really have the same focus in the two paradigms. And this also reflects on some characteristics of those different frameworks. In distributed learning, the data are distributed roughly of the same size on each client, and they are distributed i.i.d, which with that I mean that data are simply split among clients, sampled at random, independently, identically distributed. And those nodes that you send the data of let's say you split the data to are typically reliable data center, and they are sure, or you are guaranteed that you will receive a solution back from them. Instead, in federated learning, this again is pretty much the opposite, because when you distribute data, or when you have distributed clients, they will observe a different domain, because maybe I may like cats, another person may like dogs, or another one may like indoor pictures, and so on. So they will see very different domains. So data are non-i.i.d, and they will depend actually on the user habits or user preferences. And also, they're not the same size. Typically, they're modeled with a power law distribution, because I might acquire a lot of pictures, but another guy just maybe is more shy. I don't know. He will acquire very few pictures of surroundings. And as we said, clients in this case are typically remote devices, and they are unreliable. So they might have low batteries or unstable Wi-Fi connection, and so on and so forth. So you are not guaranteed that you will receive a solution back from them. That's another key point. So today's talk will focus on classical. Let's say classical is still very recent, because it's maybe 2 years old, so 3 years old, centralized federated learning. So in this case, I mean that there is a coordination of a central server. So the central server decides which statistical model needs to be trained, and then sends the initial solution to many nodes, to many computing nodes. Those nodes, distributed nodes, will then train the model that they receive on the local data. So they have their local data, they train the model, they update it, and then they send back the solution to the central server. Finally, the central server just need to, in some way, average between the model that are received back from the local clients, and this is the updated solution. And the procedure is iterated for as many rounds as needed to, let's say, convergence. All right, so this is the general federated learning framework. I will evaluate this on 2 computer vision tasks. The first one is image classification. So you just want to assign a label to each, let's say, to an image. And typically, the label you assign is, let's say, representing the object in the foreground, right? So we have a cat here or some cows there. So the label that you assign to each image is just that. On the other hand, you might have you might want for your application a more let's say more insights. So you want to know where the cat is in the image. You want to know what surrounds the cat or what surrounds the cows and so on. So you also want, let's say, a pixel-wise prediction of your image, which is semantic segmentation. You assign to each pixel of the image a label corresponding to the class being, let's say, present in that image. All right, so this was the background for today's presentation. I would like now to move to the challenges that we want to tackle in our approaches. I don't know if there are questions so far. I think so far we have just evaluated some federated learning background. So, okay, all right. So let's go on to the challenges that we want to tackle. So as you might have guessed, federated learning is quite a complicated task because you have many devices learning each its own local model on its own local data and so on. And there are still many challenges to be addressed. It's quite a recent field. I think it was born in 2017, or the first paper was from that kind of years. So it's quite of a recent field, and there are many challenges still to be addressed. Our focus will be mainly on three aspects. The first one being the system heterogeneity. We have different devices, so we have different hardware or different memory level, let's say CPUs or memory, also battery levels, or unstable Wi-Fi connectivity, or actually different connectivity, different protocols. So you have different network speeds. So they behave really different. That's the point. And we will tackle this by allowing partial solutions to be aggregated from the server. So even if a device has not, let's say, completed the local training, then could always send the partial solution, and the server will pull also this solution. Then there is another aspect that I actually like it much more, is statistical data heterogeneity. As we already mentioned, data in the local clients is highly unbalanced. So you have a different number of samples for different classes on each client. And this is maybe what I already said, that I acquire a lot of pictures, and maybe some other guy acquire a few pictures. But also, in addition to this, those pictures that I acquire are highly correlated to my preferences or my habits, right? So we have here an example where user one likes or loves cats. We all have this type of friend who likes pets, for instance. So they will acquire a lot of images of pets, and they maybe also receive some images from pet friends and so on and so forth. So they will have a tons of images of cats and dogs and so on. Then user two, in this example, maybe likes to ride a horse, and since there could be some correlation of this kind, he also may like to ride the motorbike, for instance. Well, instead, user K likes to have parties, and so maybe acquire a lot of pictures of the cocktails or going out with friends and so on. So the bottom line here is that each user will see a different domain distribution on the local data. And so we have to account for this while learning a distributed model. Finally, the last aspect, which is more kind of an issue of current federated learning optimizers, is that in general, deep learning models classify the inputs on the basis of some internal feature representations that are learned directly from the data, right? So I will actually spend some more slides on this aspect because I believe it's quite important. And yeah, existing approaches, federated learning approaches, actually disregard these internal representations learned by each client. So yeah, you all know, I think, how a deep neural network works. You have a default representation in inputs, which can be some kind of images, unstructured images. You have some deep neural network that tries to find the patterns, or like to group, to cluster the features belonging to the same objects in a similar embedding space, right? So you want to embed those default representations in input in some good semantic representations at the output of the deep neural network. And once you have done something like this, once you extract those features belonging to different objects, you can cluster, actually, you would like them to be clustered somehow. And after this, you can apply some easy task-specific predictor on top of this. So for instance, if you want to discriminate between cats and dogs, you just need one classifier, which is very simple, and a linear classifier is enough for that task. Or you might distinguish between two different types of cats and dogs, and so you need some additional, let's say, classifiers there. The point is that the better those representations are learned by the deep neural network, and the easiest will be the predictor task, which is actually what we are interested in. At the very end, we are interested in the performance of the final predictor task, right? And yeah, I believe this is pretty useful for visual applications, and we can have some visual also insights on this. But similar consideration, I'm sure they will also hold in different in other tasks, such as audio or such as yeah, different representation of the signals. So further stressing on this aspect, you typically are given a bunch of high-resolution input images. So let's say if I can have the laser point here. All right, so you're given a bunch of images in input. You feed them into an encoder kind of architecture. So you end up with some latent space, which is learned, a compact representation learned starting from those high-resolution input images. And this is typically low resolutions, at low resolution, since you are trying to encode or to, let's say, embed those high dimensional features, input space into a lower one, in order to then have some task predictors on top of them. So for instance, you can just reconstruct the original images starting from the low resolution space here. And so in output, you will have some high resolution output. Or you might have the segmentation task that we briefly mentioned before. So you have a decoder that expands back those low resolution feature maps into a high resolution output, so assigning to each pixel a class of the, let's say, of the object contained within that pixel. Or you can have some simpler classification tasks. So maybe just let's say a stack of fully connected layers, and then you have a single label prediction at the very end. All right, so another concept which we will use in today's in the works that I will present today are class prototypes. Class prototypes are nothing but the centroids of the different objects that we are considering. So since in computer vision we like cats and dogs examples, here is another one. We have cats, images of cats in input to this deep neural network, and we have images of dogs. As we said, this deep neural network should kind of encode these representations in some meaningful way. So you want them to be kind of separated. So you want the cats, the feature of the cats to be well separated from those of the dogs. And at the very end, the class prototypes are just the centroids, so the mean of these features, which is kind of some let's say representation of the object, but kind of let's say that can encode all the different examples that I have seen. So all the cats, you might recognize the cats because of the, let's say, of the shape, let's say, but also of that particular tail or those particular ears. I mean, it has a physiognomy that is peculiar of the cats. And if I show you only this example, you might surely recognize that it's different from this example over here, which is kind of that of a dog, right? So that's the main idea. You have some features that are that encode the general idea of cats and dogs. And existing federated learning approaches, to come back to federated learning, we saw that all of them disregard this internal feature representation. So most of them simply computes those weights from the local clients. So you have K clients, each of them having its own local model. So you have W from 1 to K, and then you send back to the server, and the server just aggregates the model weights as they are. Our proposed approach instead is, or our idea is to bring prototype awareness during aggregation. So we compute on each local client the set of prototypes on the local set of data, and we will send them to the server, and we, let's say, guide the aggregation process on the basis of this prototypical representation. All right, so this is the end of the targeted challenges, and I will now go through the workshop paper that we published at CVPR this year. if there are no questions. I actually don't see the chat. Oh, yeah, there is one message in the chat there.
Yeah, I just asked if there were any questions people could post.
Oh, okay. All right. So I will go on. So let me go on with the first approach that we presented at CVPR this year. The workshop is called fair averaging, and it's pretty simple. So in general, you can always express some federated optimization as follows. So you have your set of local model parameters, which are those on each local client, and you have k clients, and you want to compute simply the next step, the next central model parameters, which is this W of the next step, so T plus 1. And what you do is simply, the server simply pulls all these local model parameters, and it may optionally set some attention vector, so it's just a weighted sum in the end. So you're weighting all the local models obtained from different local clients.
Sorry, W is the weights.
Yes, W are the weights of the model, yeah.
Okay.
All right, so the first approach, which has been proposed in 2017, yeah, I was right, from Google, they simply consider this attention vector as the local frequency of samples. So the devices having the more samples, they are considered more during the aggregation process. So as you might see, devices having a lot of samples, let's say, they will tend to dominate the other ones because they will contribute more to the final aggregation. So you tend to be biased toward them, toward the models that are being trained on those devices having a lot of samples. Then let's say over the years, many approaches have been proposed. And here I only mention about FedAt, which computes this attention vector on the, let's say, as a function of the displacement of the weights, the local weights versus the aggregate weights. And what we propose in our work is very simple, because our approach was meant to just show the effect of that imbalance on non-i.i.d.ness across the different clients. So we simply set the attention vector to be 1 over the number of clients. So actually a constant value, right? All right. So I will go soon to the results. First, I would like to just mention about the dataset we use. We employed 1 synthetic classification data, a couple, actually 3 real-world classification datasets, and a couple of semantic segmentation benchmarks. What I want to focus on is actually on the distribution of all these approaches. We distribute the data or those samples to the clients according to a power law distribution. And yeah, we believe that this is kind of a reasonable assumption and is often found in the real world. So the power law, I don't know if you're familiar with that, but it means that there are some clients, or let's say a lot of clients having few samples, but there are also few clients having a lot of samples. And we distribute those data to the clients on a variable degree of non-i.i.d.ness. All right, so as we said, those data are distributed according to a power law. And I would like now to show how, let's say, this non-i.i.d.ness impacts on the, or this also distribution to local clients impacts on the final aggregation value, or in the final value you put in your attention vector there. So here I plot some aggregation values given by federated averaging, which is our baseline, and fair averaging. So for our approach, it's simply 1 over k, and if we subsample 10 clients, it's simply 0.1, right? So instead, for federated averaging, this aggregation vector, so this attention vector here, A, is proportional to the local number of samples in each client. So as we can see here, many clients in federated averaging contributes very little during the aggregation because they have some attention vectors which are maybe centered around 0. Well, here they're very low, and there are some 0.05 here. Here there are maybe 0.02, and so on and so forth. So they have very low values. So those models are multiplied by these values, and they will just bring very little contributions while aggregating a local model.
Just one question, Umberto.
Yes, please.
So we are only considering the number of updates that are being contributed by the client, no other factors associated with the client at all.
Yeah, no. In federated averaging, you're just considering the number of clients in each local data, the number of data in each local client. Sorry, that's the motivation of our approach. So what we propose is actually to change this paradigm. So first we analyze it in this work, and then later on in today's presentation, I will introduce a new, let's say, a new way of considering clients.
Much needed. Sure.
All right. So let me go on. And so we said that many clients contribute very little while aggregating these local models, and there are instead few clients, or all these clients here that tend to dominate the scene actually, because they have very high aggregation value, so maybe 0.8 against at 0.0 something. So they will tend to the aggregate model will deviate towards those models. I think it's reasonable. And the problem is that if data is highly non-i.i.d, this represents a huge problem for convergence, because again, maybe those hubs, so those clients having a lot of data, they will see only a limited distribution, right? Because we said that the distribution observed by different clients is very variegate. So maybe the hubs only see specific patterns or specific distributions. They will not see the complete picture. And to support this, we saw that simply doing our aggregation of 1/k, we can improve the accuracy with respect to federated averaging when data are distributed highly non-i.i.d. So we can see here that the orange curve outperforms on accuracy in the first row, the federated averaging. And actually, we proved this by computing also, the second clue that we observed is that using our approach, we were much more smooth toward the convergence value, right? So the curve here, the orange curve here is more, let's say, smooth, while instead the blue curve has to account for different number of clients being sampled at each round. So it is more noisy, I would say. And we proved this by computing the autocorrelation function of different lags. So here in the third row is simply a parallelogram being plotted. And we can see that the higher this value is, the better it is. So the less fluctuations there are in the accuracy curves. All right, so I don't want to spend more words on this because it was just an analysis paper to outline how data imbalance and non-i.i.d-ness is actually detrimental for federated learning approaches. I see there is a new message in the chat, so that could be a good moment if there is a question.
So yeah, I'll read it out. How does fair average perform when compared to FedBN?
Okay, so yes, FedBN is another federated optimizer, and I think we didn't test it in our approach because we just wanted to analyze the performance difference on let's say on federated averaging, which is kind of the baseline which is exploited by all the subsequent approaches. I don't remember the details of FedBN right now, but I think the bottom idea is simply to use an aggregation value which is proportional again to the number of samples in each local client, but I'm not sure. I should check it.
Would you like to unmute and go ahead, Deep? If there's anything
sure.
to discuss?
Yeah, sure. I mean, FedBN also deals with non-i.i.d data, so I was just wondering how it performs against fair average. But like, if you have not experimented, then I think
we didn't include that. I'm sorry, but I think also FedBN assumed that the attention vector is proportional to the number of local samples. Am I right?
Yeah, so the basic idea is they try to ignore the batch norm layers for the model. Yeah.
Yeah, it's true. Okay, yeah, we actually tried it, and if I remember well, it was leading to some kind of an errors in our setups because let me think. I think we tried in semantic segmentation, actually, that I will show it later, but it wasn't actually improving because batch norm in semantic segmentation is quite important. So it wasn't beneficial for our approach at all.
Thank you.
Yeah, I'm sorry. I will check the results that we obtain if you're interested. All right, so I think there are no other questions. So I will go on in to the next approach that is actually on archive and it's under submission right now. And so coming back to this slide again, we have already seen that a general federated optimizer can be embedded into this framework, right? What we propose with FedProto is simply to consider an attention vector, which is a function or a combination of two functions, one computed on local prototypes and one computed on local versus aggregate prototypes. So I will go more in detail a bit on this. So the idea is to guide our federated optimization using these class conditional prototypes that I explained before, right? So we compute on each local client the prototypical representation for each class, which are kind of the representative of the feature distributions of that each client sees. And we use a combination of two clues. One is the local displacement, which is computed locally on devices before and after local training. And so we can quantify how much each client has to adapt the model to, let's say, accommodate the local data that client observes. And the second clue that we use is the aggregate displacement, which is computed at server side between the local and the aggregate prototypes. And this kind of quantifies how much each local model prototypes move from the aggregate ones. Here, there is a warning because this aspect actually requires local prototypes to be sent to the cloud. But we believe that this actually comes with a minimal communication overhead, since prototypes are just very much smaller than the model sizes. And actually I think it's about 0.5% of the model size as an average value. And we actually believe that privacy is still preserved, since those prototypes that we send to the server are actually an average statistics of an already compressed feature representation. So we have the input images, we compute the feature representations, we compute the local prototypes, and then we can send this safely back to the server. And actually, these can also be easily encrypted, but yeah, that's not the focus of our work. There are some recent work that applies some differential privacy on top of the prototypes or on top of the models before sending them to the cloud. All right, so I have a slide with some math, but I don't want really to bother you too much with this. With the details of this approach, so I will just go very fast. The point is that like what I want to communicate is that what we defined in our work is actually to redefine the margin theory. So we are familiar maybe with the margin theory in SVM. Yeah, this is pretty similar. So you have your features computed by the local models, and you let's say compute the prototype, and then you compute the margin between the prototypes in order to have some kind of insight on how much, let's say, each local model has learned the representation of each class. So how good is the representation learned by each model. So yeah, let me go back to the intuition. Here we have, yeah, actually I've already said this. So the local deviation is kind of an hint of how much a local model has to adapt to the inner representation for each class. And the aggregate deviation instead is how much a local model has changed the representation with respect to the aggregate ones that has been learned. And as a measure for doing all this kind of analysis, we use this features margin. As we said I think we are all familiar with the SVM theory, where there is this kind of support vectors that you want to, let's say, maximize the distance between them in order to have a, let's say, faithful and robust classification at the end. And yeah, we use a similar theory where instead of the support vectors, we use these prototypes that we already observed. And yeah, we will see empirically that the centralized case maximizes this margin. And also FedProto is shown to be, let's say, that can increase the margin separation with respect to other optimizers that we consider. All right, so as a disclaimer, while our work was under submission, actually another paper with, I always call FedProto, came out. So they kind of chose our same name. But the key difference between our approach and their approach is that they use prototypes to compute a regularization term on each local client as a prototype loss. Then instead, our approach is used to compute an attention weights for aggregating local models. All right, so let me go then to some results. We have experimented, as I said, in classification tasks. We can observe here that FedProto, this orange curve, can outperform all the other approaches. And maybe, yeah, this was not very clear from the previous figure, but the small gaps, where the small gaps were not visible, but actually FedProto can win or draw in every single scenario that we consider. But more importantly, what I would like to focus in my maybe last 15 minutes or so is actually why FedProto can achieve such results. So our intent was not only to propose some optimizer that could outperform the others by considering some other clues of local models, but was also to understand why these let's say why this the framework that we proposed was actually more competitive with respect to others. All right, so to do so, we propose a set, actually a couple of quantitative metrics to elucidate this relationship between the accuracy, the margins, and this feature discrepancy of federated learning models. Actually, I see that there is another question, so maybe we can stop for a second before going to this last part.
We can take this one and end. It is more about how do we fine-tune the federated learning based models.
All right, okay.
Maybe we can take it in the end.
Okay, so we will come back to this. All right, so what I was saying is that we are interested in understanding why FedProto can achieve these results and what actually does this attention computed on the prototypes change to the aggregation of the models. So we define this metric, which is which we called aggregate mean margin, which is simply the margin computed between the prototypes, the aggregate prototypes. So we want to maximize this aggregate, this margin, because it basically means something like this. So you have your aggregate models that compute some features, and when the margin is high, these distributions are well separated. And then you can easily apply a task predictor on top, and it's quite robust. While instead, if the margin is low, you might still have some chance to draw the correct line here. So you can actually design a good classifier, but this model is more, it's less robust to some perturbation, or it has learned, let's say, a worse representation, right? So this is the first metric that we proposed, and it's simply the margin between those prototypes. So, all right, so what we observe is that the centralized case, so the centralized learning is the upper bound for this aggregate mean margin. So it means that the features learned by the centralized model are well separated, and that's why the centralized model works better, right? So it has learned very useful features, and then it's easy to apply some predictors on top of them. Then what we plot here is this aggregate mean margin for different optimizer. For instance, we consider federated averaging, FedProx, and our approach, FedProto. What we observed is that our approach was outperforming the competitors with respect to this aggregate mean margin, which means that the aggregate model learned by FedProto was separating better the internal feature representations, which is kind of a consequence of a better latent space shaping achieved again by pooling the models in a smarter way. Okay, finally, we observe that this metric also correlates with the accuracy. So the better or the higher this margin, the higher is the accuracy. All right, the second quantitative metric that we propose is this FFD. So this what we call federated feature discrepancy, and it is based on the maximum mean discrepancy that I'm sure you already observed. So you're already in contact. So the maximum mean discrepancy is simply a measure, a statistical measure to kind of determine the distance between two feature distributions. So what we said is that we consider some model A, which has some feature distributions pk of t. So this model generates those features pk of t. And then we have our reference model, which is maybe the centralized training, because we would like, so when you train a federated learning model, you would like to achieve the same performance as if it was trained in a centralized fashion, right? With all the data available at once and all the data domain distribution, let's say, known a priori. And all right, so you compute this distance between the features of a federated learning model and of the centralized model. And then we simply compute the FFD, which is the relative gain of a federated learning algorithm B with respect to another algorithm A. All right, so again, let's go back to the intuition, since I like to, let's say, go on some grounded examples. We have our, let's say, centralized reference model, which is kind of the model learned on all the data available at once. So it generates some kind of feature distribution, which might be something like this, with a good margin and all the features kind of grouped all together there in a closed Euclidean space there, in a closed cluster, in a clusterized fashion, let's say. Then we have our model A, which can, for instance, be our FedProto model, which clusters features quite well again, and can still have a good margin separation between those features learned by the different for the different classes. And then we have maybe some other model B, which is the baseline, and could be, for instance, federated averaging, which still can somehow separate the two features, but in this case, maybe the features are more or are less clustered than in the feature space. And yeah, so between them, of course, the centralized reference might be a better one because the clusters are more tight around the centroid here, and the margin separation is quite good. But if we were to choose between those two federated optimizers, I think we all agree that we would choose this one since the features are more compact. And so what does this mean is that if you perturb it a little bit, it's more reasonable that the features will still be preserved in the Euclidean space there. All right, so what we showed here in this plot is the maximum mean discrepancy of 3 federated learning optimizers with respect to centralized training. So we have our federated averaging, FedProx, and FedProto, and we compute the distance of the features generated by these 3 optimizers. Actually, okay, yeah, by those 3 optimizers. Sorry. So let's go back. We have those 3 optimizers, and we have the centralized training. We compute the distance of the features of each of these federated learning algorithm with respect to the features computed by the centralized training. So we would like features of the federated learning algorithms to be as close as possible to features learned by the centralized training, right? Because as we said, we would like our federated learning model to be as close as possible to the centralized case. And we observe this at the feature space. And what we see here is that actually federated averaging can't really, let's say, produce features which are close to those of centralized training, since this is a distance. So the higher here is the worse. And instead, our approach can minimize this distance between the features learned by federated fashion with respect to the centralized ones. And yeah, that's the main idea. as a final remark, also FedProx, which adds a proximal regularization term, can improve or can achieve some kind of latent regularization, so can achieve some features which are closer to those of federated, to those of centralized training with respect to those generated by federated averaging. So for some quantitative results, we can observe that actually our approach can match or can, let's say, maximize the margin, as we said, with respect to other federated learning optimizer, and can go closer to centralized training, which is our upper reference for the margin loss, for the margin part. And yeah, also for the MMD, we observe that our approach is closer to centralized training than competitors. All right, so I'd like now to go towards the final part of this talk, which is how then our approach behaves in a much more complex task. So we consider segmentation task, which is a dense prediction task, in which you have a lot of features belonging to different classes within the same image as well. So you might have images containing more than one class. It's not anymore as classification task where you have one single image per each class, per each task. So what we did here is to control or to have a tunable parameter alpha, which was controlling the non-i.i.d.ness across clients. So we took this semantic segmentation benchmark, which is Pascal VOC 2012, and we split this data to client according to different level of non-i.i.d.ness. So what we did is simply to have this alpha parameter of the Dirichlet distribution of the number of classes per each client. And we select this as follows. So when alpha is high, then you have an i.i.d. distribution. When alpha is very low, instead you have highly non-i.i.d. distribution. And you can tune alpha to control this degree of i.i.d.ness. What you observe from the results here on two segmentation benchmarks is that FedProto can actually improve the accuracy pretty much when the data are distributed highly non-i.i.d., while instead the performance when data are i.i.d., they are kind of the same with respect to federated averaging instead. So we don't really have a gain when data are i.i.d. So what does this i.i.d. non-i.i.d. means is that it's simply something like this. So when you have data, when you have alpha very low, so you have data which are distributed non-i.i.d. to clients, then each client sees only maybe a few classes or maybe just one class. So in this plot, different colors belong to different classes, and each row is a different client. So we can see that, for instance, the first clients here just see maybe samples belonging to one class or just a couple of classes here. So there are maybe 2 or 3 colors per row, right? So each client observes only a maximum of 2 or 3 classes, let's say, per each on the local data. When instead we go to i.i.d. case, then here the lines are more fragmented. So each client sees roughly all of the images, or let's say many samples belonging to many different classes. And where we gain is where the samples are distributed according to the user habits. So where the samples are in each local client belongs to few categories, few correlated categories. All right, so we would like now to introduce some other qualitative metrics to kind of understand how this FedProto can improve, or why this improves the accuracy. So first of all, we plot simply the auto-segmentation maps. So we have our input image here, and we split the data according to different levels of i.i.d.ness, again, as I said. And so here I report 3 different levels. And what we can see is that when data are i.i.d., okay, we can slightly improve the segmentation map. Actually, in this case, we improve it quite a lot. In this case, we can recognize the horse in spite of the cow here. But yeah, there is not a huge difference between federated averaging and FedProto. While instead, when we go to highly non-i.i.d. Data, we can observe that, for instance, the second image here has been completely misled by federated averaging, which was assigning this horse to maybe cow or sheep. while instead our approach could effectively recover the correct class, so the horse in this case. And we believe that this is actually the consequence of a better latent space organization and regularization achieved by our approach, because as we said, we drive the federated learning optimization on the basis of the features that are learned by the different, by the different models, right? So we kind of preserve the internal feature representations learned by the aggregate model in some way. So the bottom line or the effect of this is that the final classification is then performed correctly by the top classifiers on this feature space. Then, as a second metric, we introduced, actually, let's say we applied to federated learning this entropy map at the feature level, at the output softmax level. So basically, when you do a classification task and also segmentation task, you have per each pixel a score, let's say a vector, and which contains a score for each class in the data, right? So these scores can be distributed in different ways. And if you compute the entropy of those, you kind of have the guess on how much the distribution of these softmax vectors are peaked or are maybe flat. So it gives you the idea of how much the network is confident about the prediction, right? So if we observe the centralized case, ideally, we would like this entropy to be low, of course, because it means low entropy means that you have a single peak distribution of this softmax, and so the network is confident about that the prediction that is going to output on that particular pixel, right? The point is that even centralized case, even the centralized model, you have some region of the images which typically are those of the edges in this case, which are kind of unsecure because you don't really know where the class is, the cut class is finishing and the background maybe class is beginning, right? So there is some kind of, let's say, unconfident prediction in that edge pixels. Or maybe there can be some not confident pixels in some regions which maybe are kind of, for in this case, there is this the fur here of the horse that may be also representative of other animal classes. So the network cannot output a confident prediction on those pixels. Even though maybe the final prediction is good, the confidence is not very high as it was maybe in the top head here. And this is also reflected in federated learning optimizers. So yeah, this is actually what I was trying to point to with the laser. And when we go to i.i.d. data, we can already see that maybe, yeah, let's go back to this second image here. The final prediction is not very much different between federated averaging and FedProto, but instead, if you look at the prediction, or at the confidence of the prediction, we can see that actually this map generated by federated averaging is much brighter, right, than that computed by federated prototype by our approach. And this is even more true if we see on non-i.i.d. data. So here we can see a very bright map generated by federated averaging with respect in comparison to a quite low value entropy map generated by FedProto. And yeah, the bottom line is that our approach is more not only can output a better segmentation map, but is also more confident on the prediction that it performs. And finally, what we wanted to observe is the same kind of quantity, so the same entropy maps, but at the feature level. Here, for visualization purposes, I upsampled the features map to the input resolution, just for visualization purposes. So what we did here was to take the features computed by the aggregate model, to normalize them, and then compute this entropy map as we did before on the softmax output. This measure it actually gives us a hint of how representative each features is at each pixel location. So for instance, in the centralized case, we can see that the prediction of the cat here is actually based on the features of the head, as we know, right? And also for the horse is kind of the same, the head and maybe the top neck part here. So those are the most useful features for the model, which is kind of reasonable, and we have seen, I think, already in some other presentations. All right, so instead, what happens in federated learning is that those features get kind of maybe blurry. They're, let's say, you don't really understand any longer which are the most significant features. And what we tried with our approach is just to recover this kind of behavior. So we can observe that federated averaging in this case produces some feature maps which are actually, it's focusing on some unuseful, I would say, pixels here on the edge, or on the mouth here of the horse. While instead our approach is still recovering something which is related to the horse class, which is being segmented. And this is also true in other non-i.i.d. samples. So in this case, or again in this case as well. So the main idea of these plots is that FedProto can activate more similar features to those computed by a centralized training model. All right, so, okay, I'm actually about to end. So is this related to this slide?
Yes. It was related to the previous slide.
Yeah,
even
sure.
The one before that. Does this amplify bias too, along with the distance between the underlying class representations? How are these algorithms tested for fairness?
Okay, I actually didn't get the beginning of the question, so.
Yeah, can you unmute and tell what do you mean here by this?
Yeah, so I was asking that probably these algorithms have the representations have underlying bias among them, right? So if we use AMM or MMD, then does that amplify the bias too? Or if not, then what would be a way to test that? Is there something that exists?
All right, yeah, so I think I understood the question now. Actually, so we have this local data, right, on each local client. And if we don't add any provision to the federated learning optimizer, we simply disregard them. So we don't really aggregate model on the basis of the features learned by each model. What we do is to propose a new way instead to let's try to preserve these let's say the representations instead of the models of the weights. So that's the main contribution of our work, I believe. And as regard the bias, along with the distance between the underlying class distribution, I don't think there is a bias in that in those metrics, in the sense that we can have maybe a very few samples of some classes and maybe a lot of samples of other classes. But what we check instead is the distance or the margin between the prototype of those classes. So even if you have few samples for a given class and you have a lot of samples for another class, what we are interested in the end is simply the prototype. So the centroid of those features, right? So you can compute the centroid even if you have very few samples, and it will still be quite accurate, right? Because it's an average across all the different samples. So even if you have few, it will be accurate. Some future work could be to embed some other clues, let's say, because okay, now we are using just the mean or the centroid of this feature space, but what we could be interested in is also to understand how these features are distributed. So even if there are some, let's say, how is the variance? Let's say if we the easiest second order statistic we can think of is maybe the variance, or maybe how those features of different classes fit well in a different on a Gaussian mixture model, for instance. So how many Gaussians can you fit in each feature distributions, right? About the second question, how are these algorithms tested for fairness? Actually, what we proposed in our workshop at CVPR was a fair averaging. It was actually devoted to fairness, right? So in that sense, we were considering each client the same, roughly the same, actually the same, so 1 over k. So each client was considered exactly the same as all the others, even if they had or if they experienced a few number of classes or a few number of samples in each in their local data. And what we observed is with this FedProto is that at the convergence value, the attention value computed by FedProto was converging towards the fairness value, so 1 over k. And yeah, we believe that this is important because each client should be actually considered the same, right? So, or let's say each client should have at least the possibility to contribute to the aggregate model, because at the end, okay, we want an aggregate model which works well on each local client, but we want an aggregate model which works roughly well on each local client, but we would also like that the few clients which are underrepresented in the sense of having few samples are still taken into consideration. And so we believe that actually these works are more fair than actually using just the number of samples as a measure for attention aggregation value. I don't know if this answered your question, or yeah, feel free to correct me.
Yeah, no, this answers it. Thank you.
Okay. All right. So I think there are no other questions right now. No. So let's go to the conclusion. In order, to conclude this talk, I hope I convinced you that data non-i.i.d.ness and imbalanceness makes a lot of difference in federated learning optimizers, right? We proposed a couple of quantitative metrics, which are those based on the margin theory, and the other one based on the distance between the features of these federated learning optimizers and those computed by centralized training. And in addition to those, we propose a set of qualitative metrics, which I just briefly showed to you. And those are typically based on entropy maps and goes toward, we believe, towards explainability of these federated learning models. I think explainability in federated learning will be a crucial part in the upcoming, let's say, years, because again, we would like each user would like to contribute to the model, right? Or would appreciate if the aggregate model takes into consideration the user special needs, right? Or the user special habits or so on. So we would like a general model, yes, of course, that works well on all local clients, but then we might also go towards maybe personalization of federated learning models, or again, explainability to understand why some models are considered more during aggregation and why some others are considered less. And yeah, to understand also what does it happen in federated learning in general. All right, then I think I also spent a few words on feature representations, and I hope that you are now aware that those feature representations are fundamental for model training in deep learning in general. And if we want to come up with some sentence that can summarize today's talk, could be something like this. So the model, or a general model, is more than its set of weights. And typically existing federated learning approaches just only consider this set of weights, or just those distributed weights to aggregate, to be aggregated, and they disregard the representations instead that are learned by those models. And yeah, what we propose and what we believe is that future federated learning approaches should also consider this kind of latent representations learned by each local model while aggregating them. So with that, I conclude, and I would like to thank you again for the invitations, and yeah, I'm happy to answer the questions that are left behind.
Right. It was a great talk, very easy to understand. And so, yeah, there's a question. Do we have fine-tuning for federated learning-based models? Is it on a local level or centralized level?
All right, by fine-tuning, do you mean simply, let's say, training because the data are distributed, right? So do you mean that you want to train a single model on the local data without aggregating them?
No,
Or?
making it more specific to a user.
Oh, right. So you're going toward personalization then. So after you create a federated optimized model, so you do these federated learning rounds, and you end up with some aggregate model that works kind of well on each local client. Then you can personalize it further to some or to the specific clients. Yeah. Yes, this is called personalization in federated learning, because you want to target each user's each user preference or habits, right? So it is done on a local level. So you are typically given back the aggregate model, and then you typically fine tune the last layers, because they are those are the most task specific layers, right?
Right. So yeah, there's a question: is this presentation being recorded and can we watch it later? Yes, you can. I'll be posting the link everywhere on social media on Monday. We post everything on the YouTube channel. Right. And can you share the link to the slides? Like maybe you can upload them in your GitHub and mail me the link to the slides.
Yes,
Because
I will do it.
ask that in comments. Yeah.
Yeah, I will do it.
So another question would be, since federated learning is so new that the classical model is 2-year-old, what challenges do you think it still has right now? Like the major challenges?
Yeah, I think so. From the research point of view, the main challenge is still to understand how all these different components come into play, right? Because you have local training, then you have server aggregation, then you send back the solutions to the clients. So it's quite complicated, and all these different parts can be subject to some attacks, right? Some, let's say, some how do you call it, adversarial attacks, and they might want to steal your model. They might want to capture the data distribution you have on your local client. So this is still one of the major challenges. So how to ensure privacy when you transmit data, and yeah, that's one part. Another part is to understand what does it happen when you do weight aggregation based on their own. So you just aggregate weights on the basis, aggregate models on the basis of the weights, which is what all or most of the current approaches are doing. Another question is, or another crucial aspect is then how to move towards commercialization. As much as I'm aware of, all the companies now are very much interested in federated learning. And yeah, you can see many blogs from Google, for instance, but to the commercialization part, there are not so many applications, right? There are not many, let's say it's a very young technology, which is maybe 4 years old from the first paper. And so there are still no standardized ways of doing this federated learning on a commercial scale. So you want to go on a maybe global scale, worldwide. And so the key question here is that for the company, how to employ federated learning in a safe way, in a secure, efficient way, and to be able still to preserve good accuracy while ensuring privacy. And yeah, there are some public blogs I've read recently. So there are maybe the keyboard in Google, maybe there are some other applications on audio, I think audio spotlight, audio, yeah, keyword spotting, I think it was. So you do keyword spotting on distributed fashion. But yeah, so there are many companies working on that. Let's see what the outcome product will be.
Right. There's another question in the chat from Fatima. She says, hello, sorry, I attended late. What about not starting from the scratch in client and continue training, but in server starting from the scratch? I am not very clear. Could you understand the question, Umberto?
Well, I can try to summarize a bit federated learning, because I think there are some misunderstanding. So what we do, maybe I can go back to actually the slide, which is very clear here, I think. So you have only one model, which is trained or let's say you have a lot of replicas of the same model. So the central server chooses which model has to be trained, and let's say finds a set of parameters, starting parameters, so the initial model parameters, and those are transmitted to a set of collaborating nodes. Those nodes train this model on their own set of data, set of local data, and they updated the model in different ways. So for instance, model 1 is simply fitting this line in this way, the model 2 is fitting in the other way, in the other direction, and so on. Because it depends, of course, on the local data that you have. You have different data on different local clients, and so the model produced by local training is different between the local models, right? And so finally, you have those solutions. Let's say those are the outputs of the solutions, but you have the models corresponding to those solutions, and you send the models back to the server. Then the server simply computes some kind of average or some kind of more smarter aggregation. And what you end up with is an aggregate model that should work well on the different data distributions, because it's kind of the average of the models that you acquired from the different nodes. And actually, this is how one round of federated learning optimization works. And then you iterate this procedure without the step 1, of course. You simply transmit those aggregate models back to the server. Then the server updates again the solution. They send it back to the server aggregates the updated solution, and so on and so forth. So you aggregate this, you iterate this procedure for as many rounds as needed to converge. So I think this was about the question about, I'm not sure if I answered that.
Does that answer your question? Thank you. Yeah, it does.
All right.
Okay, so I guess these were the questions, and it was great hosting you. We got to know so much about a completely new domain, and I'm glad you offered to speak on federated learning instead of continual learning.
Yeah, because I saw you already had a couple of hosts or a couple of guests speaking on continual learning, so I wanted to propose something new. I mean, I think this federated learning topic has been researched from machine learning guys, deep learning communities for maybe 3-4 years, but it's roughly new in the computer vision community instead. So that's why I wanted to propose it. I think there were only a couple of papers published in CVPR this year about federated learning, and maybe one in ECCV last year. So there were very, very few papers published recently in computer vision. Yeah, but yeah, still I think it has a lot of applications also in computer vision, and so we should care about this.
Right. I totally agree. So yeah, all the best. We look forward to more cool presentations and papers from you. Thank you so much.
Thank you very much for your invitation and for attending the talk.
Thank you. See you. Bye-bye.
See you. Bye.